Okay, then we start up. So today we will have a peek into a couple of exercises, a couple of examples you find in the book by Verziger and Perich. And then shouldn't take more than an hour, I think. And then it will be guidance for exercise 1/exercise 2. Also, when it comes to tomorrow, 8 o'clock, then we will start looking into Linux. And I have brought with me, I have some memory sticks ready. So during the break, next lecture, if you want to try, see if your computer can boot, you are free to try afterwards. At least I think I have some 20 memory sticks. It takes 1 hour to create one, so I have to use the evening to create more tomorrow morning, by tomorrow morning. So tomorrow bring your laptops, preferably a Windows machine. It's okay with an old one. It has to be a 64-bit, not 32-bit. So it's not from the Viking area, but some 5 years old, that should be quite okay. For the Macintosh users, you find a cute little recipe on the home page, some 38 points recipe, how to it drops out. How to find that one. Let's see how it looks. OpenFOAM Macintosh. Your quick 38-step guide. So here you can start playing around. It should be okay. I don't have Macintosh myself, so I haven't tested it. So if you find any errors here, please tell me. But I think it's correct. So be my guest. Okay. Any questions before we begin? We are still in the world of finite difference. Simple, first obvious trial for finding numerical solution for nasty flow problems, solving the Navier-Stokes. And in the book here by Verziger and Perich, you will find, well, first chapter we have more or less covered already. Not all this detail here, but we have covered this classification, hyperbolic, parabolic, elliptic, yada yada yada, introduction to numerical method, and this you can read if you have troubles sleeping sometime. Finite difference. So here we have spoken already about the Taylor series expansion. What we haven't talked about is the other methods that exist. Polynomial fittings. You don't have to use Taylor series. You can use other concepts to find different schemes, find different recipes to get a bunch of algebraic equations. Not so important for us. So we will keep with the Taylor series. And 311, finally, an example. Also in chapter 4, he starts here with the finite volume method. We will soon jump to finite volume, yes, but if your mesh is rectangular, constant delta x, constant delta y, the equation system you end up with is identical to the one with finite difference. So actually finite volume and finite difference can be identical. So the example we find in 4.7 is just as adequate as for the finite difference. Let's see if we can find the first one. Should be here somewhere. Thank you. Here it is. Example 3.11. So I will start with this one. And it's a one-dimensional advection diffusion equation. Advection and diffusion. But it's not transient. We don't have a time derivative, so only steady state. So the equation looks something like this. You have the x derivative of density, velocity, and then an unknown generic function. It's called phi. It's a classic notation in a lot of numerical textbooks with fluid mechanics, using just phi as a generic unknown. So this phi will in general be one of the velocity components. So it could be u itself. And if it's u, well then you see here this is a nonlinear term. So it's a sort of a way to cheat. This now looks linear. One function multiplied with a totally different function, but they can be the same. So just think of it as the unknown. And now we let the small u be sort of familiar. We know him. He's not the unknown. This one equals, on the other side, x derivative of, and then we have a large gamma, and then another x derivative of the unknown phi. So this is the very general partial differential equation. So here we simplify. Let rho, u, and gamma here, of course, actually the same as the dynamic viscosity. Let them all be constants. Just to make it simpler. Then our equation can be written somewhat different. Rho and u go outside. Rho u, and then you are left with the x derivative of phi. So if you like, you can write it like this. Sub x for x derivative equals, and what do you have on the other side? Viscosity, and then double derivative. Like that. So there we have our first equation, the one to be solved. And now it's a question of discretization. For the right-hand part, the double derivative, there we have no choice. Central scheme for a double derivative. But for the first order derivative here, the advection term, that's where you can use an upwind scheme if you want to. You have a velocity in front of the derivative. Then you can start playing around with upwind schemes. In general, I would say you shouldn't, especially this first order, the very simple one. But we will still have a look at it just to see how it works. But for now, let's start with the central scheme. And in the book by Felsiger, he called it CDS, central differencing scheme. And we do it now very easy. It's a one-dimensional case, so delta x is constant. So the distance now, the position x equals index I multiplied with delta x. So The first order derivative, the advective term, will now look as follows. Rho times u times the derivative. Central space. Central differencing. So how do we write that one? Well, we need a value for the unknown on each side of the center point. So here I need I plus 1 minus phi I on the other side minus 1 divided by 2 times delta x. There you have a central scheme. Symmetric around point I. For the double derivative, well, that will now be the viscosity, and then phi I plus 1 minus 2 times the center point plus the other neighbor I minus 1 divided by delta x square. So that will now be our discrete version of the original partial differential equation number 1. Okay. Any questions so far? Should be straightforward. I choose the central scheme. Okay, then it turns out directly. We can rewrite this one a little bit. Let us we multiply with the delta x. Then he falls. Next I multiply again with delta x and divide by mu. So I will have something like this. Rho u times delta x divided by viscosity and the number 2. 2 times viscosity. And then here we will have this difference, phi I plus 1, phi I minus 1. And then on the other side we will just have the top here, I plus 1, 2 times center point, and I minus 1. Then we baptize this quantity here. This is something you should recognize. You have a density, you have a velocity, and you have a length scale divided by the viscosity. This is a Reynolds number. In the book here they call it a Peclet number because in general, this large gamma, sort of a diffusive coefficient, can be anything depending on what is this quantity. It doesn't have to be a velocity component. It could be temperature, it could be density, it could be a concentration, it could be anything. But now if we say the unknown is a velocity, then of course this is the viscosity. Hence I will call this one a Reynolds number. So rho u delta x by viscosity, I call it Reynolds number based on delta x. So call it cell Reynolds number. Or cell Peclet number if you like. That's quite okay. Now look at say the stability. We want to program this one. Of course, doing it like a matrix system should be straightforward. But if you want to do it like an iterative scheme, you have to pick one of those 3 points here. either the center point or +1 or -1, and then let all the rest be known, and then you have to iterate many times for all i's. So the center point, you only have it here. So write it on the form phi I equal to. Then what will we have? Well, here we have 1/2 of the Reynolds number, and here I have -1/2. So it's going to be a little trick here, but what you should end up with will be something like this: I plus 1, which you have here and also here. This one will now have 1. And the other one will have the Reynolds number half. Reynolds number delta half. While the other, I minus 1, well, he will have roughly the same. You will have +1 from him, but here you will have now minus. You will become positive with the Reynolds number half. There you have it. Let's see now. I want to keep the last one. So I think it's correct. No errors. Everybody agrees? Yeah. Now think in terms of stability with this max-mean method, this very crude method I showed you with just the positive coefficients. It's a little strange here to use it with a problem that is not transient. But I mean, if you want to do a programming, you could do it like this, and then just do this for all i's, and then you have to do it many times as an iterative scheme. That will work, but will it converge? Will you get a solution? Well, to use this max-mean method, max-mean, or the positive coefficient method, first you have to check the sum of all the coefficients. What's the coefficients here? Well, for this phi I plus 1, you have the coefficient 1 minus Reynolds number half, and the coefficient here, that is 1 plus Reynolds number half, and then finally 1/2 in front of all of these. And you see the sum is 1. Perfect. You can use the method. Okay. The next, demand all coefficients must be positive. Of course, the cell Reynolds number itself is a positive thing. Hence, the last coefficient here, 1 plus positive, is always positive. The problem will be this coefficient here. So this demand means that this cell Reynolds number has to be smaller or equal to 2. This is a criteria for obtaining a solution. Nothing to do with stability with respect to time. Remember the original equation, we don't have time, the time derivative was not present. But still, this is a demand for obtaining a solution at all for this steady state problem, if you choose the central scheme. And the cell Reynolds number, smaller than 2, that can actually be a quite tough demand. So it's a demand not for delta t, but a demand for small delta x. Let's call it a demand for spatial resolution. So remember the cell Reynolds number, rho delta x times velocity divided by viscosity. For a real problem, you have to use the local delta x and the local velocity in the y direction, in the x direction. And same goes actually in the y direction as well. So this has to be smaller than 2, and that can be a quite tough demand. This viscosity here can be very small indeed, so this can easily be a big number. Although delta x can be very small, that's your choice, but can come down to millimeters, micrometers. Okay, how small do you have to go to get this criteria? It can be tough. So this is something we have problems with, yes. But the demand is there, so it's quite unquestionable. Everybody with me so far? So what will be the result here? You have to use very small delta x's. You have to use a lot of cells, and then you blow the memory on your computer. That's too bad. What was the other way we could do? The other way is first order upwind scheme, which is you are not allowed to use it, but let's do it anyway. Let's see what happens. UDS. So this is now upwind diff scheme. Here we have to know the sign of this velocity in the advection term. Is it positive? Is it negative? We assume he is positive. So we sort of have to choose. Then our scheme is going to look like what? Well, the only difference here will be removing the +1 here and removing the 2. That's it. That is the only difference. So then you will have your discretization scheme very close to the one with the central scheme, but here it's an upwind differencing. It's a first order accurate only, but this then, according to the theory, should stabilize the code. Now let's see what happens. We just rewrite this one a little bit. Multiply up with 1, well, actually delta x square. You will have something like this with the viscosity, and here now phi minus 1 equal, and then on the other side as before, like that. And again, we baptize this one cell Reynolds number, and we now write it on the form phi equal. And then we get something like this. Phi plus 1, he will be here. He will have a factor of 1 in front of him. Well, then we just write phi plus 1. The phi minus 1, he will have a little bit more. He will have the 1, and he will have actually plus the Reynolds number, and this one goes on the other side, plus the cell Reynolds number. Then the phi itself, well, he will also have a factor in front of him. He will have, well, this one on the other side, that is a 2, and then plus the cell Reynolds number. So we have to divide this one by 2 plus the cell Reynolds number. So this will be now the recipe for the Upwind scheme. Again, check the stability. You add all the coefficients. What do you get? Well, here you have 1, and here you have 1 plus a cell Reynolds number, and everything has to be divided by 2 plus the Reynolds number. So yes, the sum is 1. Okay, you could use the method. Next demand, all coefficients must be positive or equal to 0. Well, that's not a problem here. We just write yes, that's the case, unconditionally. So it's stable no matter what you do. It doesn't matter. You can really make a mess out of things if you want, but you will still get a solution no matter what. No problem. Okay? Any questions to that one? Okie doke. Now to this example. It's a one-dimensional test case. So in the x direction we go from 0 to L, and our unknown phi is given one value to the left, another value to the right. And then it's a question how phi will vary in this range. And the variation there strongly depends on the local Reynolds number. This actually have it has an analytical solution. So we have the exact solution here. Now this Peclet number here is based on the entire length. Now we can rewrite that one. Let's see. Where was it? Should be here somewhere. We can see if we can find it out. Instead of Peclet number, I want to use a Reynolds number, real Reynolds number. So we have rho u based on length and then viscosity. If you now look upon a how should we then write this? Never mind. The only difference here will be if you divide the length up in the number of cells that you have. Okay, then the length scale will now be reduced to the delta x, and hence you are left with rho u delta x by mu. So that is, I mean, they're strongly coupled. They just have the different length scales. That's all. That's all. So let's do the test case. To find a solution here, I just use a direct solver, since here we sort of have checked it for an iterative scheme, but I won't use a scheme at all. I mean, we just have 3 points, so this will be a diagonal matrix, fairly easily solved with the Thomas algorithm. No problem there. So a direct method. I specify the global Peclet number, or the global Reynolds number, and then the local cell Reynolds number. You just multiply with delta x. Here, since I've chosen the length scale to be 1, so then it's fairly convenient. L is 1, then delta x will be sort of the length with divided by the number of cells that we have. So that's it. And if we now try to run this one, we get the following here. We have the exact solution. So the exact solution falls very nicely together with the central scheme here. And here I've chosen then the the global Reynolds number to be 50. So the change in the solution starts from 0. He will then have a quite sharp gradient in the end here, very sharp indeed. The Upwind scheme goes here, a little bit off, to say the least. Now if you look at the numbers for the local cell Reynolds number, the global was 50, the local cell Reynolds number is 1.25. Now the deadline was 2, stability criteria was 2. So now let's see what happens if we say use fewer cells. I go down to 20 cells. Now what happened? We get some strange results with the central scheme. The Upwind scheme, it's still smooth and nice, a little bit off from the analytical solution, but still okay. And if we even reduce the number of cells further, you will see, oh yes, this is going really, really bad with the central scheme. So you will start getting oscillatory results, and of course in a real problem he will blow up in your face quite rapidly. For the Upwind scheme is here, he will be stable no matter what. The exact solution, well, he's fairly much away from this Upwind scheme, but at least you might say the Upwind scheme is stable. Now for the values, the global Reynolds number was still 50, but now the local value is 5. So yes, the central scheme is unstable, and it should be unstable. Well, a Reynolds number of 50 is not much. So if we now increase the Reynolds number, say 500, of course it will just be worse and worse for the Upwind scheme. Sorry, the central scheme. The Upwind scheme will be stable no matter what you do. But the error is not nice. Look at the exact solution here. You have a very sharp shoulder down here. That's the correct solution. And now you have this behavior. So you might say it's not totally stupid, although the error is large. Now it's possible to find how this scheme actually behaves. How big is this error that we are introducing? And to do that, you can seek out the modified equations for these two cases. If you can recall the modified equation, that was to insert the Taylor series for this I plus 1, I minus 1, and then reorganize your algebraic equation. And if you do that, we don't have time to go through all the algebra. I'll just write down the result for you. So you can you can try to do it yourself as an exercise. Finding the modified equation for this, modified equations. For the central scheme, CDS, you will get the following. You get back your original partial differential equation, of course you do. But here you just get a second order scheme, and it will look something like what will it be? Delta x squared multiplied with phi x, and then multiplied with something more. So yes, it's second order accurate. The scheme is consistent. You just take lim, the delta goes to 0, you get back your original partial differential equation. So here it is okay. And the other, well, that's the third order derivative. For the upwind scheme, UDS, that one looks a little bit different. It looks something like this. Phi xx, and here you have a term rho u delta x half phi xx, and then second order terms as well. So with the upwind scheme, you have an outer term, also a double derivative. Well, the scheme is still consistent. Take lim, the deltas goes to 0, you get back the original equation. That's okay. So it's a consistent scheme, but it's only first order accurate. The first outer term is of the first order. And also, if you rewrite this one a little bit, you can write it on this form. Equals mu phi xx, and inside here now you will have 1 plus 1/2 of the cell Reynolds number. And then plus these even higher order terms. So there you see what happens. If you have a cell Reynolds number that is 2 or bigger, then we know this one explodes. You get very bad results if the cell Reynolds number is large. The upwind scheme is stable. Yes, that's true. But if the cell Reynolds number is 2, you have actually doubled the viscosity. So you think you are simulating water, but actually you are simulating honey or something very sticky. So that's a surprise for you. Or say if the cell Reynolds number was 10 or 20 or 100, well, then the viscosity is 101 times larger than what it should be. So, of course, using first order schemes, first order upwind schemes, no, it's not a good idea. So why do I stress so much about this? Well, first of all, you should know it's a bad idea. Second, we're going to use it anyway. A lot of code still uses it. And we are also going to use it, but we are going to use it with care. We are going to say that, okay, to get a solution here, let's start with the first order upwind scheme. It's very stable, unconditionally stable, very easy to get a solution, but we know the solution is stupid. But at least we have something to start with. So when we have received that solution first, which is then easy to get, stable, then we can switch our scheme into more advanced schemes and hopefully get a better and more accurate solution later. But we could use it as a simple starting point. That's the idea with the first order upwind scheme. That's how we are going to play around with it. So now for the exercise. For those of you still fighting with exercise 1, that is quite okay. For the exercise 2, that was reprogram the advective terms in the Sol algorithm from central to first order upwind. So I went through some of it yesterday. So I will be around then for 1 more hour here, so for guidance. Any questions? Okay, if you want to try to test your computer by running Linux, you have some USBs here that you can test it with. Okay, then I stop the camera here.